Okay, thanks for coming. You're pleased to have Jaehyeon. We'll talk about rainbow Turán problem.
Okay, thanks for coming and thanks for giving me one more chance to talk about this result. So I think most of you have heard this in Yangpyeong, or talk about this in Yangpyeong, but here I have more time, so I'll try to give more details about the motivations and how to prove it. So the problem is about finding rainbow color subgraph in a given H colored graph. I think some of you are not familiar with this kind of things, so I'll give you some motivations. So, for example, consider a simple bipartite graph like this, and suppose we want to cover the vertices in X using minimum number of edges. This is so we can, for example, use these. Okay, 괜찮네. For example, we can use this upper three edges, and we like use the middle edges connecting x3 and y8. This may cover all the vertices in X, but we have no further conditions. But if we want to find a matching, then we should think more. But finding a matching is equivalent to finding an edges like this. So we color the edges so that the edges meeting at the same vertex at Y have the same color. You can see. So those three edges meeting at Y6 have the same color, red. And if we find the edges covering the vertices in X and have different colors, then this is the equivalent of finding a matching covering X, right? Because yes, but the probable finding a matching is very well known because of the Hart theorem. So finding a matching can be considered as finding on some kind of rainbow subgraph in this kind of colored bipartite graph. And next example is a Latin square. The Latin square is the grid, and there are entries, so that at each row and each column, all the entries are different. So there are different elements in each rows and columns. And suppose we want to find some entries so that they are in different rows and they are in different columns, and also they have different entries. I mean, they have different elements. So we can, for example, find like this R and this B and this G and this Y satisfy the condition. They are in different rows, different columns, and they have different elements. But in fact, we can write this Latin square as this kind of bipartite graph. We color edges here, like here. This corresponds to row, and this corresponds to columns, and so this 1, 1 connected by a red edge means at the column 1, row 1, there is a red element, and so on and so forth. So finding such entries, which I described before, is equivalent to finding a matching here with different colors. So finding a rainbow matching. So we can consider problems which are familiar to us in finding some kind of rainbow subgraph in some kind of edge colored graph. But in this example, and in the former examples, each edge has only one color. But I would like to consider the case when each edge can have many colors. So I'll explain about our rainbow setting. Here we have a multi-graph G, And we color each parallel edges into different colors. So here, for example, we have 3 parallel edges and they have different colors, red, green, and blue. In other words, we decompose G into 3 simple graphs. And here we decompose G into G1, G2, G3. And we color each simple graph into one color. So G1 corresponds to red, and G2 corresponds to green, and G3 corresponds to blue. So it's clear. And it is natural to say that G contains a rainbow copy of this kind of length 2 path, because we can choose red edge, one red edge here, and one green edge here to form this kind of length 2 path whose edges are have different colors. The natural question which arises: what condition on this kind of color G can guarantee a rainbow copy of a given graph H? So here we find a rainbow copy of a 2 path, but we always want to find a rainbow copy of a complicated graph. We call this kind of coloring of G a simple K coloring. Here K stands for the number of colors, so in this case K is 3. And here simple means each color graph, so each red graph, green graph, and blue graph is simple. And each simple graph corresponds to a color, one color, as I said. So, we also write simply K color G like this, the collection of those color graphs. Well, this is a notion of simple K coloring, which I use. If we ignore the rainbow settings, then the most traditional problem about finding a subgraph in a large graph would be a Turán theorem, which says that if there is a graph G which has n vertices and it does not contain a complete graph KR, and also if we give a condition that G has maximum number of edges, then G should be only one structure. G should be equal to the Turán graph T r minus 1 n. This is an r minus 1 complete per-type graph, so which has maximum number of edges. So here I gave you an example of a complete graph K6 and an example of a Turán graph T5 and 15. And we call this T r minus 1 and the Turán graph the extremal graph of KR. And we write this as EX and KR. Here n stands for the number of vertices of the extremal graph. And we use the lowercase EX to denote the number of edges of the Turán graph, I mean the extremal graph. And we can also replace KR by another graph, another small graph, and then we can define the extremal graph for other kind of graph. So here is our main question: what condition on a simply colored graph can guarantees the rainbow copy of a given graph? So you can consider several types of conditions. For example, we collect the number of edges of each colored graph and take its minimum, or we collect the minimum degree of each colored graph and take its minimum, or we can just sum up the number of edges so that we count the total number of edges of the G. Of course, we give a condition that they are greater than or equal to some number, then we have some rainbow copy of a given graph. And I'll give some examples corresponding to each conditions. The first one is the traditional Untitled theorem. It says that if there's if the number of edges is greater than n squared over 4, then there should be at least one triangle. And this was generalized with the first condition. Here I emphasize the condition here. we collect the number of edges of the color graph and take its minimum. And they show that if there are 3 colors, and if this number, if this variable is greater than that number, 0.2557 blah blah times m squared, then there should be at least one rainbow, right? And you can see that the coefficient is neither 1/4 nor a rational number, but they also show that this is tight. And the second one is Dirac's theorem. It says that a graph is Hamiltonian if the minimum degree is greater than or equal to n/2. And they use thinking they use the second condition. They collect the minimum degree of each color graph and take its minimum, and show that if there are n colors and there are n vertices, and if the minimum degree of each color graph is greater than or equal to n/2, then we can find the rainbow Hamiltonian cycle. So it's a quite straightforward generation in terms of the statement. Yes. And the third one is the Turán theorem revisited. So, but to generalize this one, I want to introduce some notation. So, as you can imagine, this was generalized with the third condition, the total number of edges. And I'll introduce some notations to explain how it was generalized. So, suppose we have G, and which is rainbow H free with the given H, and H has H edges, and we want to maximize the number of total edges of the G. We can imagine 2 candidates. The first one is H minus 1 times Kn, and this consists of H minus 1 copies of a complete graph Kn, and all the other color graphs are empty, just empty. So here we have an example of 4K3. It consists of 4 triangles. The reason why this does not contain a rainbow copy of H is that if it contains a rainbow copy of H, then since H has H edges, it should have at least H non-empty colors, which is impossible for this kind of construction. It has only H minus 1 non-empty colors. And the second one is K times the extremal graph of H of size n. So it consists of K copies of the extremal graph of H. So for example, if we assume H is K4, then the extremal graph of K4 of size 6 would be the Turán graph T36, which is this. So if we draw an image of these 2 times extremal graph of K4 of order 6, it will become like this. The reason why this does not contain a rainbow copy of H, here rainbow copy of K4, is that if this contains a rainbow copy of K4, then this non-colored T36 would also contain a rainbow copy of K4, right? But this is impossible because we assume that this non-colored graph here is the extremal graph of K4. So they are very natural constructions, and please remember until the end of the talk because they will be used frequently, very frequently. So if you turn to the Turán theorem, so it says that if G ignores a copy of KR, a complete graph, then G should be a Turán graph. And if you try to consider rainbow version of this theorem, it says that if we try to ignore a rainbow copy of a complete graph KR, then that multi-graph G should be either of this or this. So this one corresponds to that H minus 1 times Kn, right? Because the number of edges of KR is exactly R choose 2. And the second one corresponds to K times the extremal graph of KR because the Turán graph is its extremal graph. And the cases.
E of G should be bigger than that. Then it's contained.
Right. I somehow miswrote it. So it says that the extremal numbers of extremal numbers are like these, yes. And the cases are divided depending on this number of colors. So if the number of colors is smaller than some threshold, then the first case occurs. And if the number of colors is greater than or equal to some threshold, this threshold again, and the second case occurs. Here, this lower t blah blah is the number of edges of this round. So they rainbow-wise generalize the Turán theorem with the condition on the number of the total edges. And this is what we focused on. So here comes again our main question. So we want to find a structure of simply k-colored multigraph which has maximum number of edges and which avoids a rainbow copy of a fixed graph. So we want to find the extremal number of edges, and we also want to find the exact structure. Here are some notations which will be fixed from now on. So G always means a simple k-colored multigraph of order sufficiently large, and the lower bound only depends on H. And H will be a graph or a multigraph with H edges. And we want to avoid its rainbow copying from in G. And K will be the number of colors. And we assume the K is always greater than or equal to H, because if not, as we saw before, G would definitely not contain a rainbow copy of H. And I introduced the notion of EX and capital EX when H and G are not colored, H colored, and we introduced the analog notations when they are rainbow colored. So that capital EX, K, and H means simply K-colored multigraph of order n, and it does not contain a rainbow H, and also it has maximum number of edges. And if we use the lowercase ex, and it means the number of edges of the extremal multigraph. So in the Keevash's paper, they considered a complete graph KR to generalize the Turán theorem. I mean, they generalized the Turán theorem, which considered the complete graph KR, right? And here we consider color critical graphs because as in the case of the complete graph, the extremal graphs of color critical graphs are very well known. So we know very well about their extremal graphs in non-rainbow setting. So it would be easier if we consider rainbow generalization of them. So a color critical graph is a graph which has at least one edge called a critical edge, such that if we remove that edge, then the chromatic number would decrease by 1. Yes, there are two definitions on the color critical graph. One is every edge should be on critical edge, and second one is there is at least one edge which is a critical edge. And here we use the second definition of which there is at least one edge which is a critical edge. And Shimovich proved that the extremal graph of an all color critical graph is actually the Turán graph. Here also is the chromatic number of that color critical graph, and this works when n is sufficiently large. So here in the left we have an example of 5 color critical graph. The red edge is on critical edge, and in the right we have a Turán graph P4n. If n is sufficiently large, then this Turán graph would not contain these 5 color critical graph. But if we add one edge, like this in one part. Then like you can put these two in here and these three in here, 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 one by one, and then we can find we can find a copy of that 5-color critical graph in this Turán graph. So this is what the intuition about why the Keevash theorem works. So the extremal graphs of those color critical graphs are very well known. And here, this is a simple interpretation of their theorem. For those, so if we consider rainbow complete KR-free multigraph, and the extremal graph multigraph should be either of this or that, either of those two natural constructions. And what they conjecture is this also holds for when we replace KR by color critical graph. So if H is an all color critical graph is H edges, and the extremal multigraph would be either of these H minus 1 times Kn or K times the Turán graph. Here the Turán graph occurs because we are considering on color critical graph, and we know that the extremal graph of a color critical graph is a Turán. And what they proved this holds for K equals 3, and we consider when K is greater than or equal to 4. So here comes our result. We proved that the conjecture holds for when R equals 4, and we also proved that when R is greater than or equal to 5, and almost all color critical graphs satisfy the condition. The condition again means it has one of those two natural constructions as their extremal multigraph. Any questions?
With the 4-color critical graphs, are we looking at H at most 4, or should H be at most the number of colors, or is that not?
H always is always the number of edges, capital H.
Number of colors is K, not 4. Oh, I see. Thank you.
Okay.
That helps. Okay, good. Yeah.
Okay, K is always the number of colors, and small h is the number of edges.
So remaining small one fraction, so we still do not know that is satisfying this condition, or is that
we don't know. So, and we also showed that we can ignore those non-color critical graphs by showing that if H is non-color critical, and if the number of colors is large enough, then there is a graph which has many edges, more edges than those two natural constructions, and it still does not contain a rainbow copy of H. So it is proved by a simple construction. So we can ignore non-color critical graphs while considering this kind of problem. So I'll now give some proof sketch. For the sake of simplicity, I'll give you one notation. So a good graph or a good multigraph means it just means that they have two natural constructions as they are extremal multigraphs. I just named it good. So there is some threshold on the number of colors such that the extremal multigraph of H is either of this H minus 9 Kn or K times some fixed simple graph G prime, depending on the size of K. And here, G prime would be exactly the extremal graph of H in a non-rainbow setting when H is a simple graph. And if H is not simple but a multigraph, then it would be somehow complicated. But anyway, this good means either of those two natural constructions or the extremal multigraph. So what we prove can be interpreted like this. So those all four theoretical graphs, and almost all theoretical graphs when R is greater than or equal to 5 are good. I introduce this good notion of good to write this simply. And rather than just analyzing the relationship between H and G directly, we somehow reduce H into HD and reduce G into GR and analyze the relationship between HD and GR. And we go back to H and G and try to say something about G. And here is just a simple interpretation of our theorem. So how to reduce H and G? Since reducing H is simpler, I'll say it first. So suppose you have H here. This is 3 color critical because we have one critical H here. And because there is 3 color critical, we can, for example, color these as red, these as blue, and these as green to make a proper vertex coloring of H. And for each color class, we make one vertex, and for each pair of color classes, we count the number of edges between them. So for example, between this and this, we have 2 edges. So here, this is the vertex corresponds to this set, and this is the vertex corresponds to this set. So we give 2 edges between those 2 vertices. So if this is 3 color critical and this will have only 3 vertices, and if this is all color critical and this will have only all vertices, so this HC has some information about the structure of H, and here it is very simple. And next we'll reduce G to GR. Here we have G, and what we use is the multicolor regulator lemma. It says that we can partition G into several parts such that for each color, so for each color, say it's blue, and for each pair, for most of the pairs, if you consider those blue edges, and they form a regular pair for each fixed color. Oh, by being regular means the distribution of the colored edges is very randomized. So this will give us some information. And for each part, so we partition G into several parts, and for each part we make one vertex. And for each pair of vertex here, we go back to G and count. And for example, if we want to add this purple edge here, we go back to G and count the number of purple edges between these 2 parts. And what if there are sufficiently many edges, purple edges, then we add purple edge here. And if not, we do not add a purple edge here. So this GR contains some information about this partition G. And the good thing of this kind of partition is that if we can find a rainbow copy of this HC in these orange parts, and then we can go back to the G and H world, and we can find a rainbow copy of this H in this rainbow part of, this orange part of G. This is because of that randomly distributed edges and the way that we reduce G and H. And this is called the multicolor embedding lemma. So if you can embed HC in GR in a rainbow way, then we can again embed H in G in a rainbow way. So this gives a method of how we, after we analyze G, the relationship between G, R, and HC, how we go back to G and H and say something. So here is the proof outline, and I think this is quite standard in the when we want to use the regulated lemma. So suppose G is a simply K-colored and it's rainbow H-free multigraph, and suppose the number of edges of G is greater than or equal to the desired extremal number. Here I did not color the edges, but please assume that they are colored. And then we use the multicolor regulated lemma to give the partition of G, and what we assume is almost all pair is regular for every color. So the edges are randomly distributed between each pair. And then we make a reduced graph GR like this. So from here we make each one vertex for each part, so that we can make this kind of GR. And what you can say is because of the multicolor embedding lemma. Right. If I say simply just if this contains HC, then this G also contains, if this contains, if this GR contains a rainbow HC, and this G also contains a rainbow H, which is a contradiction because we are assuming the G is rainbow H free. So this GR would be a rainbow HC free, and it inherits the coloring of G, so that it is also simply K colored. And we lose some density on the number of edges, but there the number of edges of GR is quite large. Here M is the order of GR, the number of vertices. And we derive somehow that GR is very similar to the extremal graph of HC, extremal multigraph of HC. So what we show is GR can be derived from the extremal multigraph of HC by adding or deleting small of M square edges. So they are very similar. And from this, what we derive that G, we go back to the GMH work and show that G is very similar to the desired extremal multigraph. So again, the difference is only small of n square number of edges. Here, this is possible because this extremal graph, this extremal multigraph, and this extremal multigraph would have almost the same structure, and that is because of the way how we derive HC from H. So we derive that G is very similar to the desired multigraph, and from this we conclude again somehow that G is exactly the desired multigraph. So I'll just say one more. So we have G, and you reduce G into GR, and we analyze the structure of GR. And we can say that GR is very similar to the desired structure. We go back to the G word and say that G is very similar to the desired structure. And we do some precise analysis to conclude that G is exactly what we desired. So here, I think all the other parts, like going from 1 to 2 and like going 3 to 4, 4 to 5 are very standard, I think. And so I would like to explain how we can go from 2 to 3. So how we can say that the structure of GR is very similar to the desired extremal multigraph. And in fact, this requires to show that HC itself is good. So our purpose is to prove that H is good, but here, to go from 2 to 3, we should also show that HC is good. The reduced multigraph is good, and I'll explain how we can show that HC is good. So first, I'll give some simple proposition. It says that if GR, so we again have GR, and we suppose the minimum degree of GR is like large enough, and if we have some small vertex set in GR, then there should be at least one vertex V such that the degree of V toward T is large enough. It's very natural, I think. So if the GR is dense enough, then you can find a vertex for whose degree toward a given set T is large enough. So we will use this to show that HC is good. So here is the simple interpretation of the proposition. And what I'll show is assuming R is 4. And I'll show that HC is good, and there are two cases depending on the number of colors. Here, first case is when K is smaller than K star. And assume that GR is rainbow HC free, and assume that the number of edges is larger than or equal to the extremal number, the desired extremal number. And what we want to show is GR should be exactly the desired extremal graph. And this condition, from this condition, we can assume that the minimum degree of GR is large enough. And if GR is not the extremal graph, if GR is not the extremal multigraph, then this multigraph consists of edges whose multiplicity is always h minus 1. Every edge has multiplicity h minus 1. So if not, there should be an edge of multiplicity at least h. So here we have one example of HC. It has 10 edges. So we add 1, 3, 1, 3, 1, 1, and you get 10. And in GR, we have at least one edge with multiplicity 10 because of this assumption. And from GR, in GR, we use the proposition to show that there is at least one vertex V whose degree toward T, our T is now V1, V2, is large enough. So this means the multiplicity of this edge, V1, V3, and V2, V3, we add them, and it is large enough. And we again set V1, V2, V3 as T, and we find a new V called V full using the proposition. So this means if we add the multiplicities of those blue edges, it is large enough. So anyway, everything is large enough. So this graph, this sub-multigraph of GR is very dense because we use the proposition. And we embed this HC in this small dense sub-multigraph 1 by 1. So first, we embed this in here, which is possible because this has at least one color, and we only require one color. Right? And next, we embed this. So because we used one color to embed the first one, we may have 6 colors left in this edge. So initially, this edge has 7 colors, but 1 color may be used before, so we have 6 colors left, probably, in worst case. But here, now we want to embed an edge with multiplicity 3, so we need only 3 colors, so which is possible. We can just simply say that 7 minus 1 is greater than 3. And we embed the next one. Now we embedded 4 colors, and we want to embed 1 more. So we have an edge with multiplicity 8. So we can say that like 4 minus 1 minus 3 is greater than or equal to 1, like, and so on and so forth. And the reason why we need an edge with multiplicity 8, at least 8, is that at the end we should close this. And this requires us to guarantee that so when embedding this edge to here, what we we probably need here we use 9 colors. So what we need is the multiplicity of this minus 9 should be at least like this one, and this requires us. This requires that the multiplicity of at least one edge should be at least 10. So this is the reason why existence of such edge implies the rainbow copy of HC. So anyway, we found the rainbow copy of HC in GR, which is a contradiction because we just assumed initially that GR is rainbow C. So simply saying we just find a dense enough submultigraph in GR and find a rainbow copy of HC in there. And the second case would be when K is greater than or equal to that threshold. Here we assume is again GR is rainbow is C3, but now in this case the desired extremal number would be K times the Turán number K3n. So this was the number of edges of triangle T3n, and we want to show that GR is exactly K times the triangle TRn. So because of this assumption, we again can say that the minimum degree of GR is large enough. So what we find is those vertices. We want to find vertices V1, V2, V3, which can act as a skeleton of the desired desired K times T3. So one property is that the multiplices of those edges are very large, so that if a vertex outside of them, say V, has large degree toward the set V1, V2, V3, but if every edge V1, V1, V2, V3 has multiplicity at least 1, then what happens is we can find the rainbow copy of HC in this graph, in this multigraph of HGR. So because of this, since we are assuming that GR is rainbow HC3, there should be at least one edge, let me call it V1, which has multiplicity exactly 0. So and in that case, we place V next to just V1, and we continue for each vertex, which has large degree toward the set V1, V2, V3. And what we can find is the partition of the vertex set of GR, which so that in each part there should be no edge, because if there is no edge, then we can find the rainbow copy of HC in some sense. And there are some exceptional sets, and what they satisfy is the degree toward V1, V2, V3 is smaller than we expected. But since we are assuming that the minimum degree of GR is large enough, like it's very large, so the exceptional set, if this red exceptional set is very small, so that we can adjust them and again separate them into 3 parts and put them in each part, so that we conclude that GR should be in fact 3-partite multiple. And since we are assuming that GR has the maximum number of edges, it should be exactly K times the triangle TRn. So we find the skeleton V1, V2, V3, and we partition almost all vertices, and we adjust with those leftover vertices to conclude that GR is exactly 3-partite multiple. So this shows that when K is greater than or equal to this threshold, then HC has this K times T3n as its extremal multigraph. And previously I showed the similar one when k is smaller than the threshold. So this shows that h is good. And I assume that r was equal to 4. And now, when r is greater than or equal to 5, what we considered are those balanced or color critical graphs. This means that if we consider an all color critical graph H, and it color reduced it. So since it is all color critical, we can partition its vertices into all parts, and we can explain how to color reduce it. And if the multiplicities of each edge of the color reduced graph is upper bounded by some number here, I wrote it down. It's upper bounded by some number, then we call the original color critical graph balanced color critical graph. So between the color classes of the original color critical graph H, the number of edges is quite balanced. And because of this property, what you can say is it is very easy. It becomes very easier to treat with its color reduced graph, and we obtain some relationship between GR and HC, and we again go back to the word in G and H, and we can conclude that those balanced color critical graphs are good. And what we also showed is most of the color critical graphs are good. I mean, most of the color critical graphs are balanced. So it says that most of the color critical graphs are balanced and they are good. So most of the color critical graphs are good. So to summarize, what we showed is all color critical graphs with r equals 3 or 4. When the case when r equals 3 was actually proved before, and almost all color critical graphs with r greater than or equal to 5, they have those two natural constructions, h minus 1 times kn or k times the Turán graph as the extremal multigraphs for this kind of rainbow embedding problem. And this kind of problems means if we focus on maximizing the total number of edges. Here, for those who forgot what they were, I gave the picture of them. And still we have the unknown conjecture. The same holds for our color critical graph when r is greater than or equal to 5. Okay, thanks for listening.
Thank you. Any questions?
Which part of the proof is the balancedness for large R?
So for those balanced color critical graphs, what we actually did is exactly this. We find small vertex then submultigraph in GR, and we just embed the color reduced HC of a balanced color critical graph in one by one grid way. And it is well done when the H multiplicity of HC is balanced, but if not, it's very hard to do this.
Can you show us the theorem 3 again? Long time ago. So this is not about the asymptotics, right? It's only about. So I was wondering whether you can say something like that with asymptotics, like everything is like quadratic, right? So n squared times something. So can you say whether the coefficients will be strictly larger?
We haven't thought out in that way. We showed this and just after that we just ignored them. We didn't consider in them.
Below is, have a quadratically more number of edges. So constant is actually bigger.
Ah, I see.
What? I think we don't know the exact constant.
Yeah, we don't know the constant, but the example written in the proof provides a lower bound. The lower bound is already quadratically
I
bigger.
see. So there's no hope of getting the analog of this stone's monovistia. Something like some determining coefficient for
Maybe,
general like instead of correct number.
maybe you can count the number of edges whose deletion lowers the chromatic number, and then that may be playing a role somehow. I don't know.
So what happens for the bipartite edge?
They also, I forgot the exact figure.
Also, is it only for the non sub-quadratic number of edges are enough to guarantee the
I forgot the exact coefficient, but
Keevash paper they also show the exact result for bipartite.
Any other things? Okay, now let's thank the speaker.